In this tutorial, we will be discussing the use of buffers. A good buffer should be able to neutralize moderate amounts of added acid or base. The effectiveness of a buffer depends on two factors: the relative amount of acid and base, and the absolute concentrations of the acid and base. A buffer will be most effective when the concentration of the acid and the concentration of the base are large. There is a limit to how much can be added before the pH changes significantly. A buffer will be most effective if the concentration of the base to the concentration of the acid, that ratio, is equal to 1. Equal concentrations of the acid and base. It's effective when that ratio is between 0.1 and 10. Buffer capacity is the amount of acid or base a buffer can neutralize, while the buffer range is the pH range in which the buffer can be effective. The buffer capacity is the amount of acid or base that can be added to a buffer without destroying its effectiveness. It increases with increasing absolute concentration of the buffer components. As the concentration of the base ratio to the acid approaches 1, the ability of the buffer to neutralize both the added acid and base improves. Buffers that need to work mainly with added acid generally have a concentration of base that's greater than that of the acid. The buffers that need to work mainly with added base generally have a concentration of the acid greater than that of the base. A buffer will be effective, once again, if those concentration ratios are between 0.1 and 10. By substituting into the Henderson-Hasselbalch equation the maximum and minimum pH at which the buffer will be effective can be determined. So if that ratio is 0.1, the log of 0.1 becomes 1. Well, negative 1. If the ratio is 10, then the log of 10 becomes positive 1. So therefore, the most effective pH range of a buffer is with a pKa plus or minus 1. When choosing an acid to make a buffer, choose one whose pKa is closest to the pH of the buffer. Buffers resist the change in pH when acid or base is added to them. Their pH does change, just not significantly. Additions of small quantities of acid or base do not radically change the pH of a buffer solution. Determining the pH of a buffer solution after the addition of the acid or base is a two-step calculation. Calculating the new pH after adding the acid or base requires breaking the problem into two parts. The first part is a stoichiometric calculation for the reaction of the added chemical with one of the ingredients of the buffer to reduce its initial concentration and increase the concentration of the other. Added acid reacts with the conjugate base to make more of the weak acid, while the added base reacts with the weak acid to make more of the conjugate base. After that, an equilibrium calculation of H3O plus using the new initial values of the concentrations of the weak acid and the conjugate base can be used. So let's go over that again. When you add an acid, it reacts with the conjugate base. These come together to reform that weak acid. When you add a base, it reacts with the weak acid with that hydrogen to form water and the conjugate base. In a basic buffer, when hydrogen is added, the weak base reacts with it to form the conjugate acid. Or with the OH is added, once again it reacts with the conjugate acid, those come together to form water in the conjugate base. So here's a visual of what we just talked about. If you add hydrogen is going to react with the conjugate acid, or the conjugate base, to produce more of that conjugate acid, the weak acid. After adding the OH, it's going to react with the hydrogen of the weak acid to produce more of the conjugate base. So for the stoichiometry part, you need to know the component of the buffer is counteracting the change. Write a balanced equation reflecting the chemistry of what is happening. Set up a table to determine the number of moles of the acid, or the base, added to the solution to neutralize the conjugate acid, or the conjugate base. And then you do the equilibrium. Write an equilibrium equation expression. Set up an ice table. Remember that ice table requires molarities, not moles, so you have to convert it back into molarity before you do it. And then you solve for the pH. So let's look at one big problem. This is actually a two-part question. You have a 10 milliliter buffer solution of acetic acid and sodium acetate. Those concentrations are 0.7 and 0.6, with a Ka of 1.8 times 10 to the negative 5. Determine the pH of the buffer. The first thing you need to do, the first scenario is to determine the pH of a buffer solution after 1 milliliter of 1 molar HCl is added. Then the second part of the question is asking you to figure out the pH of the buffer of 1 milliliter of 1 molar NaOH is added. Okay, so let's do this stepwise. First of all, you have 10 milliliters of 0.7 in acetic acid and 0.6 of acetate. We can figure out the pH of the system before we start anything by using the Henderson-Hasselbalch equation. We have the Ka. We're going to take the negative log of the Ka, which comes out to be 4.75. And then we're going to take the ratio of 0.7 and 0.6 is the base over the acid. So 0.6 divided by 0.7, take the log of that value, and it comes out to be 4.68. Now, we're going to add acid to it, which means that the acetate is going to go down, and the acetic acid is going to go up. So let's take a look at this. First of all, we have HOAC, which is the acetic acid. We have OAC and H3O plus on the right hand side. We're going to be adding H3O plus in the process. First thing we need to do is figure out how many moles we have of each. So we have 0.700 molar. It's a 10 milliliter solution. So that's 0.01 liters. Cross multiply. We have 0.007 moles of the acetic acid. The acetate, we're going to go through the exact same process. Cross multiply. And it comes out to be, you can't see that real well, 0.006. That's better. Moles. Alright, so that's before we do anything. Now we're going to be adding the H plus. So let's figure out the moles that we're adding real fast. 1.00 molar is equal X over 0.001 liters. Because I changed the milliliters to liters. Cross multiply. So we're adding 0.001 moles. Now, in that process, that means that it's going to react with the conjugate base to produce more of the acid. So that means 0.006 minus 0.001. So that means we have 0.005 moles of the acetate that's not used. And that tells us that we have 0.008 moles of the weak acid that's been formed. Now we need to figure out the molarities of these. We have 10 milliliters of the buffer and we have 1 milliliter of the acid. We're going to add those together for a total volume of 11 milliliters. That comes out to be 0.727 for the acid and 0.455 for the base. Those are now our new concentrations. We have now done the stoichiometric part of it. Now we're going to turn over and do the ice. So we go back to our other equation. This is what we're used to seeing. Alright, so according to our initial one, we have 0.727. And we have 0.455. And now we're back to 0 for the H3, for the hydrogen. So minus x, 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 0.455 plus x times x over 0.727 minus x is equal to the equilibrium constant, which was 1.8 times 10 to the negative 5. Alright, I'm going to assume that these x's are small in comparison to the actual value that's being dissociated. So I'm going to cross multiply, and that gives me 0.455 is equal to 1.31 times 10 to the negative 5. Divide both sides by 0.455. And that comes out to be 2.88 times 10 to the negative 5. I can tell just by eyeballing it that that's a much, much smaller number than 0.455. But just to show you that we do want to double check, 2.88 times 10 to the negative 5 over 0.455 times 100. And that comes out to be 0.0063%, which is perfectly fine. It's less than 5%. So now I can take this value and take the negative log of that and figure out the pH. pH is 4.54. All right, so let's do the second part. We have the exact same buffer solution, but now we're adding base to it rather than acid. Rather than going through all the steps written out, I'm going to talk about it with the information already here, just because you've already seen it once before. All right, so this time, the base, the OH minus, is reacting with the acid. Remember that when we add base, it reacts with the acid, so the acid goes down, and the conjugate base goes up. So we need to figure out exactly how many moles we have first. So we have 1 milliliter of 1 molar solution. Cross multiply, and we get 0.001 moles. We have 0.7 molar, and we have 10 milliliters, so we have 0.007, and 0.6 milliliters with 0.6 molar with 10 milliliters. All right. So the reaction itself, the change, is reacting with the acid, so therefore it's going to remove some of that acid. So it comes down to 0.006. Whereas the base here, the conjugate base, goes up. So therefore it's going to be added to 0.007. We take 1 milliliter of the base, and we have 10 milliliters of the solution, add it up, and we have 11 milliliters to be done. So divided by 0.011 to get us our molarities. From here, we're going to set up the equilibrium equation. So this is the part 2. Here's our acetic acid going to acetate and hydrogen. These are the concentrations that we got from the previous slide over here. Alright, so we subtract x from the left and we add it to the right. We're going to assume that this minus x here is extremely small, so we can throw it out. So that means we have 0.636 times x over 0.546 is equal to the equilibrium constant. So that's how we got this number here. Solve for x. So we multiply both sides by 0.546 and divide it by 0.636. Double check that our percentage is okay, so we're good. I did that by choosing the smaller of the two amounts, because the smaller of the two amounts will be a greater impact. The H plus, which is this number we then calculated, the 1.55 times 10 to the negative 5. Take the negative log of it, and we get 4.81. All right, I want to say one last comment about the Henderson-Hasselbalch equation. Remember that the relationship between the pKa of a weak acid and the pKb of the conjugate base always has to equal 1 times 10 to the negative 14. Up till now, we've been referring to the pKa. We're talking about acidic buffers. But what if you had a basic buffer? I want you to make sure to think it through. Because if it's a basic buffer, you're going to have to adjust the equation a little bit. The chemical equation for a basic buffer is written with a weak base as the reactant and a conjugate acid as the product. To use the Henderson-Hasselbalch equation for the basic buffers, it relates to pH, not pOH. The chemical equation for the basic buffer must be viewed as an acidic reaction. This does not affect the concentrations, just the way you're looking at the reaction itself. So this is what we're used to seeing. The conjugate base is on top, while the acid is on the bottom. Well, now the base is on top and the conjugate acid is on the bottom. The Henderson-Hasselbalch equation is written for a chemical reaction with a weak acid reactant and its conjugate base as a product. The chemical equation of a basic buffer is written with a weak base as a reactant and the conjugate acid as a product. So you notice that it's reversed. So the Kb makes the difference between the Ka. We can rewrite the Henderson-Hasselbalch equation for the chemical equation for the basic buffer in terms of POH rather than pH. So instead of it being the pKa, it's now the pKb here, with the conjugate acid on the top and the base on the bottom. So essentially this whole process would be the same, except instead of getting the pH, you're getting the POH. And that's how you calculate the changes of buffers.